I'll get started. So I wanted to speak briefly about specifically confidential computing for AI workloads, and not just AI workloads, how we can use it when AI workloads have to scale, right? So I was kind of looking at Karthik's slides with the first 15 minutes, and it seems like there's a lot of overlap there. So if you want me to speed up, just give me some visual indications, and I'll do that. So we will talk briefly about AI workloads and their relevance to CC. I'll speak briefly about how workloads are being scaled right now. KV cache. Difficult to not speak about agents, but only if we have the time and everyone is interested. A few slides on agents. And I'm kind of interested in having like a small discussion about the community action that we can do to move it or accelerate it even further. So I will not talk about why we need confidential computing. We saw it many times. Secure data in use. And we can do that with confidential computing. And with 1 second, I will pause here when we start talking about confidential computing with GPUs. And like Karthik said, by default, your communication from CPU memory to the device memory is in the clear over the PCIe. So when GPUs like H100 started supporting confidential computing, we can have encryption over it, right? So I will not belabor the point. So some of the classic workloads that we had for confidential computing, this is also something that we saw. Multi-party data sharing, when we talked about different banks having to share their transactional data, Bank 1 sending their transactional data into a CVM, confidential VM, and Bank 2 sending their transactional data to a confidential VM so that they can do the cross-bank transactional analysis to detect fraud. Medical diagnosis, I think this is also something that we hear about a lot. Multiple hospitals need to collaborate. Hospitals need to collaborate with pharmaceuticals to protect patient privacy. A great use case. Any kind of federated machine learning where different people are contributing the data and they want to come up with a common analysis. And on the right side, protecting sensitive data whenever we have like intellectual property involved. Especially, we have seen some examples in the EDA space. EDA, or electronic design automation, is the kind of the process to fabricate silicon, and they value their IP very, very highly. So that's a use case, PII, and so on. But what I kind of want to talk about now is that there's a very big workload, as we are all aware, that is a next generation of workload that is driven by AI. And a big chunk of this is inference and agentic workloads, and how does confidential computing fit into this space? So that's kind of what I will kind of talk about. It's not just me saying when we say inference is scaling. So this is I took a picture from the keynote by the AMD presenter. So it's difficult to see. I just highlighted the couple of key points in the picture over there: inference scaling, explosion of models, and reasoning and agent search. Right? So all of these are kind of workloads that will need GPUs. And what we ideally need to be is we should have confidential computing be able to support all of these things. Now, when we want to understand how we can scale this kind of inference workloads, we have to understand that this inference workload is not one-dimensional. Often when we think about inference, we think about like a ChatGPT-like interface. I'm typing in something, it is generating and giving the reply back to me. But that's not the only workload that we have. So these are not industry standard terms, but I try to classify this into 4 rough groups based on the performance guarantees needed from them. So we can think of like an immediate hard inference, where you have like autonomous vehicles, where you really need inference response to be really quick. And you can think of immediate soft inference. That is a bit more like what the biggest workloads that we are seeing, like ChatGPT or any kind of AI chat use case. You call up a VR, voice recognition software. It's AI behind the scenes that is doing inference on your voice. So it is not life or death if it is a bit delayed, but you still need like a pretty quick response. And you can also think about relaxed inference, where you're really okay with spending more time if you have more precise answers, right? So in medical diagnosis, that could be a case, you have your MRI images, you want to screen for something, the priority should be on precision, not necessarily getting a quick answer. You could do relaxed inference even for cost reasons. You can kind of save up your queries, spread your queries through the day. And finally, you can do kind of best effort inference. So there's also inference types, which is BitTorrent style inference projects there, where everyone is sharing their GPUs, and my query is going through multiple GPUs spread across many machines on the internet. So that is like, I will get what I get. Now, why should our community care about this? On the performance side and the trust side, many of these kind of workloads needs different kinds of trust models. So for example, the BitTorrent style example that I said, so there's a project called Petals that kind of uses this. It kind of runs GPU. It kind of shares GPU on laptops or desktops anywhere in the world. So what does confidential computing mean in that sense? So that's a question we should ask. On the other side is you can have confidential computing on-prem itself, not even on the cloud. So there are situations where who you trust and what your workload is will determine how you use CC. And your performance trade-offs obviously has to be different in your the real-time versus the most relaxed inference cases. Trade-offs are different. And there's also a difference in attestation semantics. So especially who is responsible for attesting to what. I will talk more about that in a bit. And finally, the GPUs themselves. So you have single GPU, you have multiple GPUs on multiple nodes. All of this affect how you run your workload in CC, right? And not just from the performance side, what we should also care about this, because we want to enable new projects that support all of these different use cases, right? Not just a single type of workload. And from what I have seen right now, the state of art that we have is we have a lot of turnkey solutions. What I mean by turnkey solutions is if you are an enterprise and you want to use confidential inference, you often go to a vendor that will tell you, send me your queries, we will host your model, we will make sure it's hosted in a trusted environment, we will take care of attestation for you, you just get reply and the guarantee that your queries are safe. Now, that is great, but we cannot be limited by just that model, just these turnkey models. We should also be able to provide support for build your own models. So I should be able to lease VMs myself. If I want, I would like to kind of create my own clusters, set up my own attestation servers, so on and so forth. So that kind of provides for a more vibrant and more open ecosystem, and it is often a better fit for many corner cases. And even often, it could also be much more cost effective, right? Okay, so when we talk about scaling inference, we can talk briefly about the different configurations we might have our TEE. So you can have your standard VM with a single GPU, multiple GPUs, and then for proper AI workloads nowadays, you also need to think about a multi-node, a cluster of nodes, each having a single GPU, or each having multiple GPUs. We will not talk about the single GPU case because this is about scaling. And in order to talk about how CC should work for these things, we should briefly understand how parallelism works for AI now, right? So we have a couple of different parallelism modes. I will not go over all of them, but just to briefly touch upon tensor parallel, pipeline parallel combined, which is a combination of tensor and pipeline, and expert parallel and data parallel modes. So just to, we don't have to get into the AI details of it, but just to give you a flavor. Now, before I talk about this, I would also like to mention something else Karthik mentioned, which is bounce buffers. So you have your encrypted CPU memory, and what you essentially do is you lease some memory from the unencrypted space, and essentially the problem is that your CPU RAM is encrypted. You just move that encrypted data to your GPU. The GPU doesn't know what to do with it, right? So you essentially lease some memory in the unencrypted space and create a bounce buffer, and then you encrypt the data that you want into the bounce buffer, and your NVIDIA driver will kind of move that data from the bounce buffer to the device and make sure it is in the clear in the device, ready for your processing. So why am I talking about this in reference to parallelism? Sometimes the data load time, when you load the data from CPU to GPU, the time taken could be higher, right? Or when you go from disk to CPU, CPU to bounce buffer to device, time taken can be higher. So there is more protocols coming up soon where you can avoid this bounce buffer problem, where your CPU and GPU can be in the same trust zone, and you don't have to go through the bounce buffer. Essentially, you can think of it as whatever encrypted memory is in your RAM, your GPU can kind of see it, and vice versa. Right? I think there's support for some of this already from AMD SCVTIO and Intel CDX Connect. And I think the Blackwell processors will support it, but we still have a lot of H100s in the market, a lot of people using it. So back to parallelism and and why all of this is important, right? So when we talk about tensor parallelism, so we can think of AI model. What you do is you kind of split the tensors into different GPUs. So some of the tensors will be in GPU 1, some in 2, 3, and so on. Oh, the second one should be 2 there in the figure. So the idea here is that you do your for transformer models, when you find attention and when you're trying to predict the next token, you are essentially doing a sequence of matrix multiplications. Here's a very simplified example. You have a 2x3 matrix being multiplied by a 3x2 matrix, resulting in a 2x2 matrix, high school math. The real tensors are much bigger, much higher, with much higher dimensionality. And in this case, if it is tensor parallelism, what would happen is that you can see that the blue matrix has been split into 2 columns. And one of my GPUs, GPU 1, has the first column, and GPU 2 has the second column. And I do the multiplication, and then I combine the results with a gather. Now, the reason why I'm talking about this is that I'm trying to answer the question, when should we use tensor parallelism to scale AI workloads? You can use it when the model is very large to fit into a single GPU. But ideally, you should use this only when you have very fast GPU to GPU interconnects. If your GPU to GPU interconnect is slow or not as fast as what NVLink and NVSwitches will give you, this whole process of splitting and gathering is too performance bottleneck. The performance would be not good enough. So when you have multiple GPUs in the same VM, if you have multiple GPUs in the same VM and they all can talk over NVLink, then this is great, right? So I was trying to find the last couple of days whether it is possible to kind of lease a VM in one of the clouds where I can get more than one GPU in the VM, and I couldn't find anything. So if someone else is familiar of this option available right now, let me know. But I was looking at the specifications of the VMs offered in Azure, And this is a CVM that I can lease. It has 40 vCPUs, but I can only have one H100 in it. So right now, I don't think there's a commercial offering where you can really get multiple GPUs in a single VM. So there could be other potential offerings, and maybe we will soon have at least offerings with multiple GPUs in the protected PCIe mode at least. But now what do? I need to, what's my goal here? I need to scale my inferencing. I need to use tensor parallelism, but I'm kind of stuck, right? So one option I can go with is I can lease multiple TEEs, each with a single GPU. Now, I talked about the importance of the GPU to GPU interconnect. It has to be really fast for my tensor parallelism scaling to kind of work. I may be able to get around if I have InfiniBand, but if I'm limited to using network sockets or if I don't have NVLink, and this is not ideal. So I can think of a second option, the pipeline parallelism mode, which is essentially, you have think of the same AI model, and now what I'm doing is, instead of splitting it horizontally, I'm kind of splitting it layer by layer. When I'm splitting it by layer, I would essentially load one layer in one GPU, or one or more layers in one GPU. And in this example, I have layer 1 in GPU 1, 2, 3 in 2, and 4 in GPU 3. So what the benefit of this is that it kind of reduces the communication you need between GPUs. So it is, when your bandwidth is lower, it is better to use pipeline parallel models. And it's better suited when you have multiple nodes, each with a single CVM. And there are also, so we kind of talked about this already. Now, the main question I want to ask us is, the current non-CC community has a set of recommendations on when to use tensor parallel, when to use pipeline parallel. Do those recommendations still hold when all our workloads and scaling kind of shifts to CC, right? So for some of the examples of some of the workloads, the trade-offs are very similar. So for example, processing time versus batch time. You can kind of see that the CC and non-CC mode is kind of pretty similar. But if you want to do a lot of model loading and unloading because of the overhead of bounce buffers, our performance overhead of non-CC is kind of higher. Performance overhead of CC is higher. But I'm not trying to point at any specific problem, but we have to be aware of these new trade-offs, and then our community should be ready with recommendations on kind of what to do, right? And similarly, on the right side, this combined parallelism. Combined parallelism, essentially, what it does is you combining tensor and pipeline parallelism. So you imagine you have multiple nodes, each with multiple GPUs. You use tensor parallelism within a node with multiple GPUs, and across nodes, you use pipeline parallelism. You can also use expert parallelism, which is when you have mixture of experts model, you would host each expert model in each GPU. That's kind of an option. Data parallel is the simplest one, where you have the same model loaded in multiple GPUs, and it kind of go on. All right, so that is kind of the first thing where I kind of talk about inference parallelism and how CC affects it and why we should be aware of it. Second thing that we have to worry about when workloads move to CC is KV cache. So I tried to kind of create a simple image, ask the AI to create a simple image that summarizes what KV caching kind of looks like in AI inference. It kind of gives you very unrelated, not unrelated, so to speak. It gives you an image. You can see that there are some it has picked up some pieces. It knows that KV cache makes things fast. There's kind of like a car there, and it knows that it's got something to do with tensors. There's some tensors here, and so on and so forth. But if you can figure out what KV cache is from this image, best of luck. This is, by the way, this is also using an AI model a couple of years back, I think 2023 version of a model. I tried the same query in the latest current model. I'll show that image in the end. But very briefly, what KV cache does is, what KV cache is that in transformer models, in autoregressive transformer models, you generate tokens. And once a token is generated, when you are generating the next token, so you have token 1 to generate token 2, you have to find attention of token 1 also. So in other words, you have to make sure that the token that was last generated is also sent through all the layers of your transformer models, along with all the previous input. So that's an oversimplification, but what that means is that to generate token 2, there is substantial overlap in compute to generate token 2. And I can use some of my GPU memory to cache the results from my token 1 generation, which can speed things up faster. Especially, I'm caching 2 key matrices, a key matrix and a value matrix, hence the name KV cache. So it gives us a lot of speed up, but the size of the KV cache also grows linearly. So there's a portion of your GPU that has to be reserved for KV cache. And it also grows linearly with the sequence length, so how big is the context that you're sending to your model. But what's also happening now is that when when inference services are being tuned or are being kind of made for multi-tenant users with a much longer and longer context, we are starting to reuse KV cache in many different ways. We are not just caching the current token to the next token key and values. We are also caching keys and values from prior inputs, or if you have, let's say, system prompt, which you send again and again, those things also you are caching. So the point I'm trying to make here is that there's a trend where we are moving these KV caches from individual GPUs to a common store, which could be across a GPU, a DRAM, and your local disk. And every time you are moving data out of your GPU to somewhere else, you have to kind of keep track of your performance, the same kind of graphs that we saw. And when we also start thinking about KV cache sharing across multiple tenants, you may also have to rethink about what is your attestation and trust models. So this is the same query. I asked, create an image that summarizes KV cache and AI inference. This is the same image that I asked to the latest and greatest model, and it gave me this. It is a way better representation of what KV cache is. So I think we can all be kind of happy with the changes that's happening and be more convinced that there's a right workload for us to promote confidential computing. Okay, so before I kind of talk about agents, I guess for our community, I think a couple of things. We can discuss this, or if you have comments, please feel free. So the AI inference system communities, they are very active. They move very fast, and their projects are very performance-focused and ease-of-use focused. And is this the right time to engage more closely with them? And what can we do? So we can kind of create playbooks, which can help with multi-GPU inference and some of the problems that I mentioned. How can that be addressed, or have a point of view on how to address this? And we really need people with AI and systems and security skills. So I was kind of wondering, maybe a special interest group for confidential AI. I don't know. So I will just briefly talk about another workloads, another way agents are being scaled with using AI agents. There's a lot of definitions for agents. It's very nebulous, but I essentially consider an application to be agentic if it's the AI that decides the application flow, control flow, right? So in this example, imagine you do have agents, and then you want to scale the number of tools these agents are using. And I have like a rough example, which I showed in the CC Summit, I believe, where imagine this agent is calling a couple of tools, a box tool in this example, and an HR agent. So HR agent has access to some sensitive data. And maybe there are more tools being invoked, like a tool that does some business policy summarization or a data sanitizer, so on and so forth. And when the scale of these agents and tools increase, it is very easy for us to kind of say that, hey, let me put all of this in a confidential computing box and we can all be happy, right? But the reality is that we can't really, that is not the way people are looking to scale. That is not how you can scale. Often it is a mix of things. There are some that is still on cloud, there's some on-prem. You don't want to put on CC for whatever reason. Some can be on cloud and so on. So again, the question to be asked is when should we put all the tools in confidential computing environments or some tools in it? Should there be updates to the agent communication protocols which can tell, hey, this tool should run in a CC, or don't invoke this tool unless it runs in CC. So these are areas where we can really engage with other communities here. One last point, when we talk about scaling confidential clusters, one more thing we kind of have to think about when we scale clusters is when we add new nodes to existing clusters, how do you want to handle it? One option is that I can say, I give this responsibility completely to the owner. So owner here, I mean that there's a cluster owner. This cluster owner has set up some confidential VMs, and they have created a confidential cluster. An AI workload is running in it. And in this case, everything is fine, that's okay. But imagine a situation like I have a Ray cluster, and then I have a Ray head node, and there's some confidential nodes are already doing the compute, and a new node is being added. Do I just trust the owner? As far as the Ray head is concerned, when a new request is coming in, should I just assume that that node is good and add that node to the cluster? Or should the Ray head process demand the new node produce attestation measurements which are verified before the node is added to the cluster, right? So it depends on the responsibilities, the responsibility of the Ray process, or just the responsibility of the cluster admin or the owner who is trying to add it. So these are some questions that we also need to answer. There are also projects that can run your entire Kubernetes cluster in encrypted mode. The Constellation project is an example. So there are things that we have to think about here as well. Okay, finally, what else can we go wrong? Can we just put our workloads in confidential environments and be happy? That's as secure, but especially for agentic workloads, we still have to take care of hallucinations or prompt injections, right? So imagine you have a AI agent, and the agentic tool, the job of it is to generate some code and execute the generated code. But if the executed code is, if the generated code is opening a network connection, then whatever you do, you put it in CC, you open a network connection, it doesn't help. So you still need your protections against hallucinations and prompt injections and the new attack vectors with the confidential AI brings us. So I'm almost done. I'll summarize here. So in this thread of what else do we need, especially when you have Kubernetes or other control planes that manage your confidential AI, you can think of what responsibilities does the control plane have. Does it have too much power? You can try to separate some of that out. And attestation and verification services, which is such a key part of confidential computing. How does it scale to this large number of agents and tools? And my application code itself, so I can attest to the firmware, I do secure boot, but then if I keep dumping a whole bunch of unverified third-party libraries and software onto my TEE, everything I did so far is kind of wasted. So there are maybe you can start thinking about IMA, which is a Linux subsystem for measuring file integrity during runtime. and software supply chain techniques, so to kind of ensure that not just your lower layers, but even up to your application code and everything is kind of verified. So in summary, do AI need sensitive data? That is where we, or the confidential computing, can really shine. We can say, hey, we can deliver sensitive data to AI workloads in a protected way. And for us to really say that we can support all AI workloads, we should have the ability to scale these AI workloads in the same way non-CC workloads can scale. And there are still some things that we have to do. We still need a better user and developer experience. And GPU CC is still growing. We have one vendor, NVIDIA. There are other GPUs that I don't know if and when if they will support confidential computing. And these are the things that we can work towards and look forward to. So that's all I have. Any questions? I'm happy to answer. Otherwise, that's all I have.
Who wants to start? I'll start then. Sure. So first of all, the idea of a confidential computing consortium SIG on confidential AI, you're not the first person to suggest it. I think the way to do it is to come to the TAC meeting and maybe show this presentation or something like it and say, look, there's lots of stuff we need to do. Right. And I think the TAC is going to be very interested in that and may well. You just need to gather enough people who are interested, and right. I don't think that's going to be very difficult, I would hope. Sure. The other thing you said was about the agent-to-agent communications. Right. And just this week at OSS North America, a new Linux Foundation sub-project or sub-foundation was created or announced called A2A. And being led largely, I think, by Google, and I think there's some great opportunities to engage there. I've already reached out, in fact, because I think that's really interesting. Yeah. Loads of really interesting things I want to talk about in this talk, but anyone else have anything they want to raise before? No? Can you go back a few slides, please, now? Sure, sure. Be a few things I want to... this one is a particularly interesting one, I think, for me, around attestation. Mm-hmm. We tend to think of attestation as a singular thing. We do it once on a single TE. As we add GPUs, we know that already becomes more complex. We need to think about more than one component being attested. And of course, there's lots of layers of things you might want testing there. Then you might want to think, well, I might want to test more than once for a particular process, even in the simple case. And people think about that a bit, but that becomes complex as well because memory pages change, you need to decide which bits you hash, whatever. I know there's been some talk within the CCC, I haven't been following it, on layered attestation, which I haven't been following particularly. But when we start talking about this, about dynamic attestation and trust models, it becomes very, very interesting. And yes. I, for one, want to have lots of conversations about this and draw lots of pictures. So I certainly would welcome this discussion happening in the CCC, and I think there's going to be lots of other people who are interested.
Yeah, definitely. So I can put together some more details and try to share in the mailing list, and then it would be a good place to start, maybe. Yeah,
well, and we'll get you presenting this, and or even multiple bits of this, because sure. That's very, very interesting.
Wonderful.
Any other questions? Oh, here was one. Yep.
So first of all, I'd like to sign up for the mailing list, wherever it is. And can you go to where we said CC is not just CC is not enough, the three risks that I want to understand.
I think that was later.
Later, yeah. So, just before this.
Sure.
Yeah. Where there was this hallucination. Yes, this one. Yeah. So I think insecure coding practices, I think your example cleared it up that, you could open a port. Sensitive data, so the confidential computing is posed as a mitigation strategy for sensitive data. So how is that a risk?
So this is more in the context of agentic workflows. Imagine there's a tool that is generating code, this tool is being hosted inside a confidential VM, TEE. But what this tool is doing is this tool is generating code to be run locally. Imagine the situation.
To give on?
This tool is generating AI-generated code to be run in the CVM, in the TEE.
Okay.
So this is code which I have not attested. I don't know. The AI is generating this code.
Okay.
Now, if the AI is generating this code in a way that it is sending the code itself or something in my CVM to someone outside, then that is a scenario where confidential VM is not going to prevent it, right? So this is
So basically, you've got an AI-generated covert channel. So there's some interesting demo given by someone, Jacob Legeros, I think, from Ulyssion, who gave a demo at the CCC recently, where, yes, you can absolutely have AI exfiltrating data itself. This isn't being
Right.
taken from the outside in. It's coming basically from the inside out.
correct.
Yeah. Even if you can help that happen by the way you ask questions from the outside, it's actually the application which is in some way giving out data
Correct.
externally.
Right. So this is not violating any of the confidential computing principles. It is just that the behavior of the application has been changed to send code out. It's almost like saying, I want to run an application that exfiltrates data in a CVM. So that is kind of so when we start thinking about deploying AI agents, then these are things that we have to keep in mind as well.
Any other points that anyone would like to? There's so many things to go into in further detail. It's a really good survey of some of the things we need to worry about next in this area. Very thought-provoking.
Yeah.
Thank you very much indeed.
All right. Thank you, everyone.
Yeah.